we're going to explore a slightly different topic, a couple of ideas relating to sequences and summation, both ideas that come up a lot in computing. So last unit we had talked about formulas and evaluating them, and we'll return to some of these ideas again when we talk about functions later on. But when we're dealing with computing, very frequently we are dealing with these discrete numbers, most often things like the positive integers. So again, the positive integers, you've probably seen this idea before. It's just the numbers 1, 2, 3, 4, and so on. So if you're doing something like in a loop or a repeated process, you have the first step and then the second step and the third step and so forth. You can, again, usually you'll track that with like an index in like a computer program. Sometimes you might start counting at 0 instead, but again, 1 is a great place to start. So the name that we give for a sort of list that proceeds sequentially with a first thing, a second thing, a third thing, a fourth thing is a sequence. So a sequence is a list of outputs called terms for each positive integer input. So again, we will see expressions like this, little formulas that tell us what kind of expression we're working with. So here we have find the first 4 terms of the sequence, and you'll see the notation here we're using is a, and then this little subscript n. So we might say a sub n. The formula for that is 1 over n squared. Here we're starting at a sub 1. So the process here is kind of just like we saw with formulas before. We're really just plugging things in. So when you see a sub 1, it means you're replacing you're replacing n with 1. So 1 over 1 squared, which you could also write as 1. A sub 2 would mean replace n with 2, so 1 over 2 squared, or you could also write that as 1/4. A sub 3 would be 1 over 3 squared. 3 squared is 9, so 1/9. And then a sub 4 would be 1 over 4 squared, or 1 over 16. Now, this is one way of writing these things out. Very frequently when we see sequences, we see them written as a comma-separated list. So like 1, comma, 1/4, 1/9, 1/16. And frequently in computer science, we run across these formulas that don't have a specified endpoint, so they could keep going on and on. So you may see it written like this. You could also, if you were to continue this pattern, see it written with these like ellipses that says basically the pattern continues. We'll do a couple of similar examples here. So next up we have the sequence b sub n, which is 2n minus 1. We're going to start it at b sub 1. Again, that just means we start plugging in the value n equals 1, and then we go to n equals 2, and so on. So we can use that same notation we did before. So 2 times 1 minus 1, that's 2 minus 1, so that gets us at 1. b2 would be 2 times 2 minus 1, or 4 minus 1, which is 3. b3 would be 2 times 3 minus 1, 6 minus 1, which is 5. You can kind of see the pattern that's happening here. b sub 4, 2 times 4 minus 1, equals 7. So when we think about this list that we've just made, 1, 3, 5, 7, it becomes pretty apparent what's happening here, right? We can note that these are the positive odd integers. Again, in computing, especially if we're like designing some sort of a process, we might want to keep track of something different to do when it's even versus when it's odd. So this pattern of 2n minus 1 skip counts basically over all the even numbers and just produces odd numbers. And here, again, with this particular expression, when we start counting at n equals 1, it produces all of the positive odd integers. So it's a useful thing to note. Let's look at another thing. What if we have n as part of an exponent? So if we have -1 to the nth power, and we want to write now the first 5 terms of this sequence. So again, the principle is exactly the same, right? We're just replacing n with each of these positive integers. So -1 to the first power, we recall our exponent rules, and anything to the first power is just itself. Anything squared is it times itself. If we do -1 times -1, we know that we get a positive 1. Now, as we get to progressively higher powers, you could think about breaking this up using your exponent rules, right? You could know that this is the same thing as -1 squared times -1. We already found -1 squared was positive 1, so if we multiply that by -1, you get to -1. You might see where this is going, right? C to the 4th, -1 to the 4th. Note that our result is just whatever we had before times -1. So if we multiply that previous result by -1, we get back to 1, and then C5, when we take -1 to an odd power, then it gets us back to -1. So again, if we want to think about like writing out this pattern, we can see what we call an alternating sequence, where it's alternating between a negative and a positive. So again, this is also a very kind of useful idea if we're trying to switch off between positive and negative. There's similar ways you could have something like switch off from 1 to 0. But anytime you're at an odd position in there, it's -1. Anytime you're at an even position in that sequence, you get positive 1. So you could figure out something much further down, the 14th, for instance. So just as a quick little check, if you had C14, to ask a question sort of beyond what we just did, if we took -1 to the 14th power, well, since 14 is even, taking -1 to an even power will get us a positive 1. So that's the basic idea behind a sequence. Another related idea is what we call a series. And a series is what we get when we take a sequence, and then we start to add up the successive terms of that sequence. And another name that we give for this thing is a partial sum. So a partial sum means add up a bunch of these terms of a sequence. And specifically, the nth partial sum would mean add up the first n terms of that sequence. So the one that we just gave, Cn, which is -1 to the nth power, we noted that the first 5 terms were -1, 1, -1, 1, -1, right? So those are our first 5 terms of the sequence. The partial sums are going to be adding up the first n of those. Again, sometimes it's hard when we're thinking about these things broad. Let's make a concrete number, right? So the first partial sum just means the total of the first term. It's kind of almost a little silly when you're doing a first partial sum. It just means the first term that you have. All right, so the first term listed in the sequence is -1. The second partial sum is going to be the sum of the first two terms. Well, we start with -1, we add 1, and we'll get 0. So the second partial sum is 0. It's the sum of the first two terms. The third partial sum, again, is going to be the sum of the first three terms. Again, our sequence starts with -1, +1, -1, so that works out to be -1. Once more, we can kind of see that pattern, right? The fourth partial sum is going to be the sum of the first four terms. Since we've already written out these terms, all we have to do is add them up. We can note they kind of pair off together. We get a fourth partial sum of 0. And then lastly, if we do our fifth partial sum, we just throw in that last -1. We already know the sum of the first four is 0, so if we subtract 1 from that, we get -1. So partial sums means we're taking a sequence, we're adding up progressive terms of that. Now, and this is like usually if we're trying to like keep a running tally of something, like when we're executing a loop in a programming context, then a partial sum is kind of that thing that's keeping track of this of each of the terms and adding them all up as we go. Now, the nth partial sum means we add up all of the first n terms, but another thing we frequently do in computing is add up some certain number of those terms. Maybe not starting at the first term, maybe starting at the 10th term or something like that. So if we see a sequence and we're adding up those terms of that sequence, starting at m and going up to n, the way that we do this is we're going to have to keep track of which term it is that we're talking about. So here's where the notation gets a little trickier. We want to start at m and end at n. We're going to first use this Greek letter, this capital sigma, and sigma stands for sum. And the thing that we're adding up are these terms a sub whatever. Now, to describe that whatever, we need a new variable, what we call an index. So k here is our index of the sum. And it's just keeping track of which number we're on. So our index k is going to start at the first value that we have. So we're going to write that here. K starts at m, so k equals m at the bottom, and then it's going to go up to the top at n. So we would say that this sum has a lower limit of m and an upper limit of n. It seems very abstract, but I promise it's actually not that complicated. We'll look at this example here, find the value, and you see this sum written out like so. Again, depending on textbooks and software, you may see the sum represented slightly differently. You could also see it represented again with an index here on the bottom at its starting value and its ending value. And then here's the expression that you're working with. So the 3i plus 1 gives you your rule, the rule that determines the terms that you are adding up. So really all you have to do when it comes to working with this summation notation is keep track of your index, see where it starts, and then just keep adding 1 to that index. So again, there's lots of ways to keep track of this. If we want to keep track of this in total detail, we could note here that our sequence, I could label it a sub I. We could note that that sequence that we're adding up to get the sum here follows a pattern, and we could find all of those things here, right? A sub 1 would be 3 times 1 plus 1, or 4. A sub 2, 3 times 2 plus 1, or 7. A sub 3 is 3 times 3 plus 1, or 10. A sub 4, 3 times 4 plus 1, which is 13. A sub 5, which is 3 times 5 plus 1, or 16. And finally, a sub 6, 3 times 6 plus 1, which is 19. Note, by the way, there's a pattern here where they're increasing by 3. Not coincidentally, that is the coefficient here, the value in front of I. So these are all of the values that we would get if we just replaced I with 1, 2, 3, 4, 5, and 6. So noting that, our summation notation is just going to tell me to add up all of these values. So we'll get 4 plus 7 plus 10 plus 13 plus 16 plus 19. So again, it's the same sort of idea as a partial sum. Here we did, in fact, happen to start counting at 1. We could have counted somewhere different if it said I equals 2. But here, our summation expresses this value. And you'll note it actually has a little some pairing we can take advantage of. 4 plus 16 is 20. 7 plus 13 is also 20, so that's 40. And then 50, and then another 19 will be 69. So again, our expression here, this sum works out to be 69. We've got one more page of this section. Again, it's a pretty short section, mostly just trying to introduce some notation here. Let's do another summation. Here we have a sum, n equals 0 up to 3, and the expression that we're working with is 1 plus 1/2 to the nth power. Here, I'm going to jump right into the writing out all of these things together and throw in some parentheses just to make sure that expression is kind of unambiguous. So this is, if we think about how many terms are there going to be altogether. At first our instinct might be 3 because that's where we're ending, but if we actually start counting at 0, there's one extra 1. So there's going to be 4 things altogether. So if n is 0, we've got 1 plus 1/2 to the 0. If n is 1, we've got 1 plus 1/2 to the 1. Anything the first power is just itself. And then 1 plus 1/2 squared. And then finally 1 plus 1/2 cubed. And just replacing the n with the values starting at 0, ending at 3. And then we're going to take the sum of all of these things. Might be helpful to clean up this expression. Note the parentheses aren't really needed anymore because it's just addition. So you got 1 plus 1 plus 1 plus 1. Remember, anything to the 0 power is 1, provided it's not 0. And then we've got 1/2. 1/2 times itself is a 4th, or you can square the top, square the bottom. And then if we cube the top, cube the bottom, we get 1/8. Note that the first part is 5, And then if you want, you can think about these as eighths would be your common denominator here, 4 eighths, 2 eighths, and 1 eighth. So that's 7 eighths altogether. Of course, if we want to write this as an improper fraction rather than a mixed fraction, because the notation can be awkward, it can be tricky to input that into a homework system, for instance, we could write this as 40 over 8, which that's what 5 is, plus 7 over 8, or 47 over 8. And remember, you can use calculators for simplifying here as well. I'm choosing not to, but feel free to do that if it makes you get a more accurate answer and avoids any sort of computation errors. So that's our basic overview of working with sequences and working with summation notation. The one other thing that we frequently do in computing is try to go backwards and start off with a pattern and then try to pick up on what's going on in that pattern. There's a lot that we could say about this. I'm going to have a very just brief introduction of these things, and if you need to know more about them, you'll encounter them in a future class. So here, suppose we've got the sequence 2, 2/5, 2/9, 2/13, and so on and so forth. We're just trying to pick up on what pattern appears to be the case here. You might notice, right, the 2 seems to be common. I've got this 5, 9, 13. We can note it looks like that's going up by 4, right? And in fact, right, sometimes it's useful to rewrite a whole number as a fraction. In fact, a lot of times with sequences, leaving things in unsimplified form kind of reveals a little bit more about these patterns. So once we realize that part, it looks like we, again, assuming that this pattern is continuing, we're not going to have any tricky things on here. It looks like we have a fraction where that numerator is always 2, and then the denominator is increasing by 4 as we go. So the next number, provided that that falls into that pattern, is still going to have a numerator of 2, denominator is now 17. Next one, numerator is going to be 2, denominator is 21, and then last one, again, if we keep adding 4 to the denominator while the numerator stays at 2, it'll be 2 25ths. Another kind of sequence here, we might see -1, 2, -4, 8. There's another pattern that's going on here, and we can note it looks like at each step, first off, it's switching sign from negative to positive and back and forth, and it's getting twice as large in magnitude. So if both of those things keep happening, then double 8 and make it negative, you'll get -16. Double this again, right? We love our powers of 2, so it's going to be 32, positive this time, and then -64. There actually are ways that we could describe a formula that would give the nth term of this thing. If you're curious about that, we can note that this type of sequence is called a geometric sequence. Actually have a lot of applications and properties. But again, I'll just introduce the name and you can explore that more as needed. One last problem. Let's go ahead and come up with a formula for a simple case. We want to describe the even positive integers. So we want to, again, kind of working backwards, start off with our sequence and describe it using a formula. So 2, 4, 6, 8. We've kind of seen this before, almost, with the odd numbers, right? With the odd numbers, we go back to that one, that the odd numbers were given by the expression 2n minus 1, right? If we started counting at 1, then that produced 1, 3, 5, 7. Well, the only difference between even numbers and odd numbers is that the odd numbers and even numbers are offset by 1, right? If we had skipped this -1 part, then we would just have 2, 4, 6, 8, and so on. So in other words, if we can just cut out that -1 portion, we will have what we want. So the sequence that will describe our positive integers is we take our input n, and then we double it, and that's it. All right, again, in a sequence, our inputs are only positive integers, so we're only plugging in 1, 2, 3, 4, and so on. Again, this type of pattern where you're like skip counting or where your numbers are separated by the same amount each time also has a name. This is an example of what we call an arithmetic sequence. We could talk about these more, like I said, but we're here just kind of introduce the ideas of sequences and sums because it's very frequent things that we encounter during the exploration of computer processes. So with that, that concludes this section. Have a great rest of your day.